in section 3. The only difference is instead of one variable, now we're in two variables. If you think back to this, in Algebra 1, you did graphing, inequalities, two variables, but almost all of them were linear. In fact, in Algebra 1, I'm sure they were all linear. You graphed a line, solid or dotted, and then what did you do? Shaded, because it's an inequality. So first thing you figure out is what type of a line do I need, solid or dotted? How do you tell? If it's greater than or less than, we use a dotted boundary. And if it's less than or equal to, greater than or equal to, we use a solid boundary. The second thing you've got to figure out is, where do I shade? And to figure out where you shade, the easiest way to do that is pick some point that's not on the line or the boundary and use that as a test in your original inequality. If it works, shade towards that test point. If it doesn't work, shade the other side of the boundary. Jump over the fence and shade the other side. This is the same as what you did in Algebra 1, same as what we did in Algebra 2, except Algebra 2 we sometimes threw a quadratic or an absolute value inequality in there. But your answer is your graph. And on a pre-calc, we're eventually going to throw some cubics and quartics and things like that in there. Y is greater than x squared minus 2x minus 8. What's the general shape? Parabola. What do you need to know to graph it? The vertex. So the parent graph is y equals x squared. The translation vector or vertex is going to be, how do you find the x coordinate? Negative b over 2a. So the opposite of negative 2 over 2 times 1 is going to give you a 1. When you plug in a 1, what's y? What is it? Negative 9. That's your translation vector or your vertex. What's the vertical stretch factor? 1. Now, last period, there were kids who said, yeah, can't we just factor this though to find the roots? Yes, you can. But I don't really care about the roots in terms of graphing this inequality. I have to have the vertex. If the roots are nice, pretty factorable roots, that's great to get them, but I'm going to get them anyway. Is this boundary going to be solid or dotted? Dotted. So the first thing I do is I plot the vertex at 1, negative 9. And then I use my parent graph and my vertical stretch factor to find the next point. Since the vertical stretch factors are 1, we're going to behave the same as the parent graph. Right 1, up 1. Right 2, and right 3. And there's one of your intercepts, x-intercepts. Not that I care. I mean, I care, but I don't care. Left 1, up 1. Left 2, up 4. And left 3, up 9. There's your other root. What kind of a boundary is it? Dotted. So make sure you connect with a dotted line. What should I use as a test point? 0, 0. That's always going to be the easiest, unless you go through 0, 0 with your graph. If you plug in 0, 0, these things all become 0. 0 is greater than negative 8. True or false? True. True. So I'm going to shade so that I cover 0, 0. Use a highlighter. You're going to need a couple of different highlighters for this. That graph what your graph looks like? Where's the solution? What point is the solution? All the bluish green points. So just write solution right in here. That's all I'm looking for. Make sure I can tell that this is a dotted boundary. Right, don't make that a mystery. Don't come up to me after the test and I marked you down and wrote -1 dotted and you say, well, Mr. Lockwood, if you hold it up to the light, you can see, look at how it glances off. If I have to hold it up to the light to see that it's dotted, it's not dotted. Make it crystal clear that you're talking about a dotted line. All right, try this one. Or these two. This time you have a parabola, the linear. All right, so y is less than or equal to 4 minus x squared. That is a parabola. Vertex is at 0, 4. It's horseshoe down, and vertical stretch factor is -1. So you should have that parabola, and it's solid. When you plug in 0, 0, is it true or false? True. So we plug in 0, 0. It should be like this. Okay. The other one's a linear equation. It goes through the point 0, 2, that's the y-intercept, and has a slope of 1. So you should get this dotted boundary right here. If you plug in 0, 0, true or false? That one's false. So we want to shade the other side. The other side of 0, 0. Give you something. Oh, really? Like this. Okay? So right here, we're going to write solution. Okay? Anyone have an issue or concern on this? Okay. X plus 3 greater than 2. This is two variables. How many variables do you see? One. So which variable? We see x. What does that tell you about the graph? Yeah, it's not an that would have to have a y in order to get the V shape. There's only one variable. Yes. More. Oh, what? How do you know? And the variable is x. When it's x equals vertical line. If this was the one variable y, what would we get? Horizontal. What do we get when we have absolute value greater than? Is that an and or an or? Absolute value greater than is or. That means you're going to have opposite sides is your solution. If it's absolute value less than, then you have in between. How do we evaluate absolute value x plus 3? Yes. So x plus 3 is greater than 2, and the opposite of x plus 3 is greater than 2. Here you get x is greater than -1. When we solve this, we get x is less than -5. Here's -1. Here's -5. They're vertical lines at those points. x equals -1 and -5. The shading greater than -1 is to the right. 0, 0 makes it true. When you plug in a 0, that's true. When you plug in a 0 here, that's false. So we're going to go to the left of this boundary. If your graph looks like mine, I'm going to take a point off. Okay? It's hard to tell whether those are solid or dotted to me. This one for sure looks solid. So your graph, you need to be able to tell that it's a dotted boundary. Don't make it a mystery. Any questions on that one? You would have solution in both. So here's your solution. And here's your solution. The solution part, writing it in there, just helps me know that you have identified the solution. Try this one. So if we look at this, y minus 3 is less than or equal to 6, and the opposite is less than or equal to 6. Here you're going to get y is less than or equal to 9. Here you're going to get negative y plus 3, less than or equal to 6. And y is greater than or equal to 3. Okay? Negative 3, thank you. So we want solid boundary at negative 3 and a solid boundary at 9, 2, 4, 6, 8, 9. If you plug in 0, 0 with the less than or equal to 9, that's going to be true. So you're going to be doing this. All down here. When you plug in the 0, 0 for the negative 3, that's going to be true also. And we're going to be doing this. And we're concerned with the overlap. The overlap is pink and blue in here. So this is your solution. Oh, rainbow. Okay? Question on that? I could live with you just doing in between.
So if it wasn't true, it would be like away from the
Correct, like this one. So this one, for example, 0, when you plug in the 0 with respect to the negative 5, 0 is less than negative 5. That's false, so we go this way. Whereas the 0 is greater than negative 1, that's true, so we go towards that point. Okay? Try this one. First thing I want you to know is I'm not going to give you the factored form. I'm not going to give you this. I want you to be able to go and factor out the x to the quadratic and then factor it to this. Okay? So once you have that, you can identify your roots. What are your roots going to be?
0,
0, 0. The lovely and talented 2/3 0 and negative 3 0. So graph those, are we going to be solid or dotted? Solid. So we're going to have solid intercepts at -3, at 0, and at 2/3. Okay? What's the degree? Degree is 3, it's odd. And the leading coefficient is positive. So what's the end behavior? Down on the left, up on the right. And we're going to do something like that. Are we not being nice? I think so. So now you need to pick a test point. It doesn't matter. You can do cover your eyes and go, boom, I'll take that test point. But you're better off picking something that's easy to work with, like 0, 0. Oh, we can't pick that one. So how about 0, 1? If you plug in 0, 1, this whole side of the state becomes a 0. 1 is less than or equal to 0. Is that true or false? That's false. So we want to shade on the other side. So we're going to shade down here. So all down here. Okay? Yeah. Okay, let's not overanalyze the smiley face. Jeez Louise. Has anybody got a question on this? All right, let's look at the vertex on these. So the top one, the vertex or the translation vector, opposite of b over 2 times a. What's the x-coordinate of the vertex? Thank you. Get a calculator out if you can't do it in your head. What's the y-coordinate of the vertex? 2 1/4. So at -0.5, -2 1/4, you're somewhere in here. How do you get to your next point? From the vertex. How do you get there? Right 1, up 1. Right 2, up 1, 2, 3, 4. And if you want to go right 3, you can go up 9. Left 1, up 1, left 2, up 4. And you might have intercepts at 1 and -2. I don't really care. It doesn't matter to me. It's a solid boundary. If you plug in 0, 0, is 0 less than or equal to -2? True or false? Usually false. So we're going to shade on the outside. It will be all of okay. For the second one, where's the vertex going to be? 1/2. What is it? 12 1/4. 1/2, 12 1/4 is going to be way up here. And then vertical stretch factor of -1, so it's right 1, down 1, left 1, down 1, right 2, down 4, think we'll be about right here. And left 2 down. So your graph's going to look like this. How about 0, 0? That's true. So this one's going to shade on the inside. So you're trying to find out where the overlap is. The overlap's going to be in this dark blue area, and that's where your solution is going to be. Any questions on this? Okay. Breathe.